Okay, today we will solve 5 easiest problems from AIME 1993. We will start with the first one. As you can see, it's a very short problem and it will be a very simple one as well. How many even integers between 4000 and 7000 have 4 different digits? Well, here we have two main requirements. At first, we should look at even integers, and integers that we need have 4 different digits. Well, what can be the final digit if we're looking at even integers? So the last digit should be 0, 2, 4, 6, 8. So these are options for the last digit. However, we also look at the integers from this range. Well, let's start from 4000. If the integer looks like 4000 and then we have 3 other digits, well, definitely the last digit should be one of these. However, we have 4 different digits. 4 is already taken, so 4 is out of the game here, and we have only 4 different scenarios for the last digit. It should be whether 0, or maybe 2, or maybe 6, or maybe 8. And so we can choose among these options. And we have also these 2 digits here. Well, we can start from this one. Are there any restrictions? Should it be even or odd? We definitely don't care. It doesn't matter. The only thing that all 4 digits should be different, but in general, here we can have any number, odd or even, and here also any number, odd or even. There are no restrictions for us. The only restriction that now we should care about all the different digits. So it's very easy to calculate how many options do we have. Here we have 4 different options to choose the last digit, so 4 times. How many options do we have to choose this second digit? Well, in general, we have 0, 1, 2, and so on, 9. So in general, we have 10 options for the digit on the second place. However, 2 numbers are already taken, this one and this one. So 2 numbers, for example, this one and 4 are already taken. It means that you are left with 8 possible options. So you have 8 possible scenarios for the second digit. And when it's taken, for example, we took it as maybe 1, how many options are left among 10 digits? Well, obviously you are left with 7 possible options for this position, for the third position. And this is it. 4 times 8 times 7 is the total number of these numbers that consists of different digits. So if we look at the numbers like 4000 and something, then you have 4 times 8 times 7 possible scenarios that the number at first is even, and then it consists of different digits. So let's calculate here. 8 times 7 is 56, 56 times 4 is 224. Okay, so let's remember this number. Now we consider the next range from 5000 to 6000. If we look at the number that starts from 5, and here we have 3 different digits. And as you can see, 5 is already taken. So what about the last digit? We should have even integer, so the digit should be one of these. And now all these options are possible for us. 5 is not an even number, so there are no restrictions. We can take any of these as a last digit. So it can be 0, 2, 4, 6, or 8. So we do the same mathematics here. 5 options to choose the last digit. Well, how many options do we have now to choose this second digit? Again, we have 10 numbers, 10 digits, and 2 of them are already taken. 5 is taken and the last is taken. How many options left? We have 8, and for the last digit, that is on the number 3, we need to choose this one. We also can take any digit. However, 3 options here are already occupied, so it means that we have 7 options to choose this one. Therefore, here the number is 5 times 56 is 280. 280 is our number here, 280. So 280 numbers that look like this. They start from 5, the last one is even, the last digit is even, and they consist of different digits. And so let's here emphasize. And finally, we are looking at numbers that start from 6, and it will be the last step because we need up to 7000. So if we consider numbers that look like this, it will be our final step. So here should be even number at the end. However, 6 is already taken, so we have only 4 options: 0, 2, 4, and 8. 0, 2, 4, and 8. And using the same mathematics, we have 4 options for the last digit, then 8 options for the second digit, and 7 options for the third digit, and we have the same number of options: 2 to 4. 2 to 4, let me mark here 4, and eventually to find the total amount of numbers that work for us, we add these 3 numbers: 2 to 4, 2 to 4, and 280, and the result will be 728. If I'm correct. So 728 is the total amount of numbers from 4000 to 7000 that consist of 4 different digits that are also even. 7 to 8 is the correct answer for this problem. Okay, we can go to the next one. Okay, we go to the second problem, problem number 2. During a recent campaign for office, a candidate made a tour of a country which we assume lies in a plain. On the first day of the tour, he went east, the second day north, and so on. Basically, when you have problems like this, it makes a lot of sense to mark these directions. So you make a small picture on the side, and here, for your convenience, you mark that north is here, south is here, west is here, and east here. So we assume that it is initial position just before the trip happens, and on the first day he went east, so we should mark this direction, so he goes to the right. On the second day he went north, so something like this. On the third day he went west, and on the fourth day he went south, and on the fifth day he went east again, so something like this. And if they tell us etc., it means that the pattern will continue. It means on the next day he will go like this, on the next day he will go like this, and so on. So the trip will go in this cyclic manner. Basically he will go along these segments on each next day, and you know how it happens in general. But after that we're also told that if the candidate went n square over 2 miles on the nth day of his tour, so it means that on the first day of his tour he traveled 1 over 2 miles. On the second day of his tour he traveled 2 square over 2 miles. I don't calculate this number for purpose, so I will leave it like this. And third day he traveled 3 square over 2 miles. On the fourth day he traveled 4 square over 2 miles, and so on. And we are asked how many miles was he from his starting point at the end of the 40th day. So as you can see, with every day the distance that he travels increases, and it increases significantly. For example, on the 5th day we have 5 square over 2 miles, and eventually on the 40th day, which is the last day of his trip, he will travel 40 square over 2, because this number is already 1600 over 2, which is 800, and this one is 1 over 2. So we started from half and finished on 800, so the travel increases significantly. And after that we should redraw our diagram. So we can see that he travels in this cyclic pattern, but it's very important that the distance increases. So it means that, let me draw it for example here where we have more space. So he starts here. At first day he goes to the right, just a very short distance, 1 over 2, and on the second day he goes like on a larger distance here, and here he travels like larger distance, and on the next day the distance even larger, and again the distance even larger on the next day. So the distance increases, and he is traveling like this, and you can see that he is traveling on the pattern of this expanding spiral. It just follows from the condition. So we know the direction, that it goes whether to the right, to the left, up or down, and the distance increases every day. So, and he traveled like 40 days, and we need to find how far he is from his starting point at the end of his 40th day. So the starting point is here, let's mark it as S, and the end point is here, so it will be our final point, and we are looking to find this total distance. Okay, so probably it's not exactly correct with this diagram. His final point will be a little bit lower, but for us it doesn't matter, so we understand the pattern, how he travels. And in order to find the length of this segment, we should understand how to solve this problem, what approach will we use here. So when I worked with students, usually students understand that they should maybe add some distances that go horizontally and add some distances that go vertically, but most of students try here to work with just pure numbers. So they try to maybe add this one, subtract this one, add this one, and eventually they care about that the distance should become positive, because the distance can be negative, and it creates a lot of confusion, a lot of problems. In order to solve this problem normally, you should simply introduce coordinate system, because if you have coordinates, it's very easy to find the distances. You have a special formula, right? So if you know the displacement, for example, from some point, the displacement is delta x along x and delta y along y. In coordinates, it's one displacement, another displacement. Then the distance is given by the formula square root of delta x squared plus delta y squared. And when you work with coordinates, you do not care about the sign of numbers. It can be positive, negative, you just don't care. It's very convenient for us. So here we have x-axis, y-axis, of course it is a region, and we have these distances here. So the first one is delta x1. This one along y, we will call it delta y2. This one, it's the third distance, so it will be delta x3, just because it's along x. This one along y, it will be delta y4. This one along x, it will be delta x5. And this one along y, it will be delta y6. This one along x, it will be delta x7. And this one along y, it will be delta y8. And as you can see, in terms of delta x, we have only odd numbers here, delta x1, x3, x5, x7. And along y, we have even numbers, 2, 4, 6, and so on. Let's understand how to calculate the total displacement. For example, with respect to x. At first, we go delta x on the right, and after a while, we go delta x3 to the left. So the distance, the total displacement is delta x1 to the right with a plus sign minus delta x3 to the left. So because it's opposite to the x-axis, if it's opposite, we get it with a minus sign. If it's along x-axis, we get it with a plus sign. So delta x1 minus delta x3, again, to the right, along x, we get plus delta x5 minus delta x7, and then we have here plus delta x9 and so on. So we understand the pattern. And if we continue this pattern, it will be plus delta x9 minus delta x11 minus delta x11 and so on. When will we have to finish? You see, we go along odd numbers, and the final distance is delta 40. So, and as you can see here, the last two numbers should be plus delta x37 minus delta x39, obviously, and probably the last distance will be like this, will be vertical. Okay, so what is this sum numerically? So we know the formula that delta xn equals n square over 2. It's just by a condition. So it means that we have 1 square over 2 minus 3 square over 2 plus 5 square over 2 minus 7 square over 2 plus 9 square over 2 minus 11 square over 2 and so on. Plus, and the last sum here will have 37 square over 2 minus 39 square over 2. If you use difference of squares here, you will see that in each case, for each separate sum, the difference between these numbers will be equal to minus 2. So minus 2 is the common factor here everywhere. 1 over 2 I will just factor out. Right away, 1 over 2 is a common here. This difference will be minus 2 times for the sum of numbers here. Here, the sum of these numbers, the difference is -2, the sum is 12, plus 12. Here you have the sum of 20, and the next one you can see you jump plus 8, so the next one will be again plus 8, plus 28, and so on, and we will finish on this one. So the sum of these numbers will be 60, 69, 76. So let's check that everything is correct. The distance between 76 and 4 should be divisible by 8, because every jump here is exactly plus 8. So the difference is 72, and it is divisible by 8. So what we have here, it is an arithmetic sequence. The first term here is 4, the difference is 8, and how to get this total sum? We will use very simple formula. The first one plus the last one times how many terms you have divided by 2. So the first one plus the last one divided by 2 times how many terms we have here. So we told that this difference, 76 minus 4, is 72, and when we divide it by 8, we get 9. So it means that we have these 9 jumps. Each jump is of length 8. We have 9 jumps like this. Each jump leads us to a new number, but besides these 9 numbers here, we also have the first number 4. So in total, we have 10 terms in this progression. So this one is 5, and 80 times 5 will be 400. 400 is the total sum here, and this one cancels out, and the total sum is minus 400. So the total displacement, delta x total, which is the sum of these smaller displacements, is minus 400. Well, good enough. Eventually, we need also to find delta y, the total displacement along y. And here we will use the same idea. When we go along y-axis, we add delta y with plus. When we go opposite to y-axis, we add with minus. So the total sum that reflects delta y displacement is delta y2 minus delta y4 plus delta y6 minus delta y8, and so on. So you understand how it works, and eventually if we need to finish on 40, the last sum here will look like plus delta y38 minus delta y40. And again, we look at the sum numerically, so this one will be 2 squared over 2 minus 4 squared over 2 plus 6 squared over 2 minus 8 squared over 2 plus and so on, and the last sum will be 38 squared over 2 minus 40 squared over 2. Perfect. Again, we factor out 1 over 2. We use formula for the difference of squares for each of these differences. Again, the difference of each numbers here is simply minus 2, so it will be minus 2. It will be factored out of each of these differences, and the sum here is 6, the sum here is 14, and so on. Obviously, the next sum will be again plus 8 will be 22, and so on, and the last sum here we will have 78. And again, each jump here plus 8, and if we calculate it correctly, the distance between 78 and 6 should be divisible by 8, which is obviously the case. And how many numbers do we have here? We will need it eventually. 78 minus 6, 72, divided by 8, it is 9, so it reflects that we have like 9 numbers here, and it is the 10th number. Again, we have here 10 numbers in total. These two like cancel out, so we will have minus sum of this progression. And this sum is the first one plus the last one over 2 times how many you have? It's 10, so it is 5, and this is 84 times 5, which is 420. And the total displacement is minus 420, so the total y displacement, so delta y total, equals minus 420. Therefore, we know that finally, the final position of our traveler will be somewhere here, because delta x total is negative and delta y total is negative. So eventually, after 40 days, our traveler will end up somewhere here in this portion of the plane. And in order to find this total distance, we will use this formula. So we need to find square root of 400 squared plus, I will get rid of minuses right away, plus 420 squared. Again, in order to find this distance, we will work in a reasonable way. Of course, we will not square these numbers, no way. We will get this one as 40 times 10, and this one 42 times 10. 10 squared, we will factor it out, and then 10 will appear here. So it will be 10, and here we will have 40 squared plus 42 squared, like this. Okay, so what about these numbers? Let's continue factoring out some numbers here. So for example, 40 is 4 times 10, and 42 is, so it will be squared. 42 is 2 times 21, so 2 squared, 21 squared. Well, unfortunately, we can only factor out 2. So here, 40 squared, I will represent as 2 squared times 2 squared, because it's 4 squared, right, times 10 squared, and 2 squared can be factored out of both of these, and 2 will appear here. So it will be 20 square root, 2 squared, maybe we will leave it like this, 20 squared. This one is 20 squared, and this one is 21 squared. Unfortunately, nothing can be done here more, because they don't have any other common factors, and we need simply add these numbers. And when you add this, it will be 400, 441, it will be 20, 841, and 841 is very close to 30 squared. 30 squared is 900, and obviously you can notice that this one is simply 29 squared. So this one will look like 20 times 29, which is 400, plus 9 times 20, plus 180, so the total distance is 580. So the right answer for this problem, that at the end of the 40th day, the traveler or the candidate will be on the distance 580 miles from its initial position. And it concludes our solution. So let's go to the next problem. Okay, and the next problem that we will solve will be number 5. It is a simple problem related to polynomials. So we have a polynomial p0 of x. It is a polynomial of the 3rd degree. It looks like this. And we have a formula for integer n greater or equal than 1. Pn of x equals Pn minus 1 of x minus n. And we need to find the coefficient of x in p20 of x. So initially it looks a little bit confusing, especially this formula. Well, in order for us to clarify the process, we should write this formula for certain values of n. And of course, the minimal value of n that is allowed here is 1. So we will write that p1 of x equals p0 of x minus 1. What does it mean? It means that polynomial p1 of x is defined through polynomial p0, but instead of x, you should substitute x minus 1. So instead of variable x, here you substitute x minus 1. So p1 of x looks like x minus 1 cubed. Instead of x, I substitute x minus 1 plus 313 x minus 1 squared minus 77 x minus 1 minus 8. That's how this polynomial p1 of x looks. So before you decide to expand everything, so you should understand how the process will continue, because sometimes if you do such expansions, you do just a very, it's a very bad decision. Like in many problems, if you get some numerical values like 720 times 121, you shouldn't multiply it right away, because in many cases it will be easier to work with numbers. And here you have the same situation. You do not need to expand it. You should look at this process. How will it continue? So for example, for n equals 2, p2 of x equals p1 of x minus 2. So it means that the polynomial p2 of x is defined through this polynomial if instead of variable x, we substitute x minus 2. So p2 of x equals x minus 2 minus 1 cubed, because x minus 2, it's instead of x for us now, right? So plus 313 x minus 2 minus 1 squared minus 77, x minus 2 minus 1 minus 8. Okay, great. So now this polynomial looks like this one. And once again, before you subtract these numbers before expansion, it makes a lot of sense to look what will happen next, because sometimes you will do like a very bad job if you try to simplify everything before you understand the complete process. So let's go to the next step. P3 of x equals P2 of x minus 3. So P3 of x is defined through P2, but instead of x, we substitute x minus 3. So P3 of x equals x minus 3 minus 2 minus 1 cubed plus 313 x minus 3 minus 2 minus 1 squared minus 78 x minus 3 minus 2 minus 1 and minus 8. And obviously you understand clearly what will happen next. We need to go up to P20 of x. We can tell right away that P20 of x by using like similar ideas. If we look at 3, here we have 3. If we look at 2, here we have 2. So P20 of x will must look like this: x minus 20 minus 19 and so on minus 1 cubed plus 313 x minus 20 minus 19 and so on minus 1 squared plus, I'm sorry, here we have minus 77 x minus 20 minus 19 and so on minus 1, and finally minus 8. Obviously, you see here that we have an arithmetic sequence, so x minus sum of the arithmetic sequence. The sum of numbers from 1 to 20 equals 1 plus 20, the first one plus the last one, over 2 times how many numbers you have here, 20. So this is 10, and this sum is 210. So this one can be substituted by 210. So P20 of x equals x minus 210, all of that cubed, plus 313 x minus 210 squared minus 77 x minus 210 and eventually minus 8. Okay. So that's what we have. It is a final look of your polynomial. We need to find the coefficient of x for this polynomial. And of course, you don't need to expand it. You need to just get all the coefficients that are related to x. So from here, you should only get the coefficient which looks like something times x. From here, you should take coefficient that looks something times x. And from here, the coefficient that looks something times x, and after that you add these similar terms and you get the value of the final coefficient near x for this polynomial. So here, this formula a minus b cubed, it looks like a cubed minus 3a squared b plus 3ab squared minus b cubed. And we need with x, so x here is this term a, so this term will have x and 210 squared. So this coefficient near x here will look like 3. Here we have x instead of a, and this one will be 210 squared. It is the coefficient from this expression related to x, plus here related to x we have only double product. Double product from this square will be 2 times 210 times x times 313 with minus sign. So the next one will be minus 2 times 313 times 210. It's just double product from the square. 313 is this multiplication from here, and here we have x. So these are two terms from this, and finally we have minus 77x and nothing else. So we separated everything related to x from each of these expressions, and x factors out, and we have a sum 3 times 210 squared minus 2 times 210 times 313 minus 77. So here, once again, we don't need to multiply it because it's much easier to work with these numbers like they are. So because we can factor out 210 here, and what happens that here we have 3 times 210 minus 2 times 313, and after that minus 77. And here, this one is 630 and this one is 626. Perfect. The difference is simply 4. 4 times 210 is 840 minus 77. It is the total difference in this parenthesis. And the result obviously is 763. 763, and the total coefficient in front of x is 763x. And if we are looking at the coefficient near x, it is definitely 763. So 763 is the right answer for this problem. So this one is considered to be solved, and we're going to the next step. Okay, let's go to the next one. It will be number 6. It's a very beautiful problem, and in the same time it's pretty short. So what is the smallest positive integer that can be expressed as the sum of 9 consecutive integers, the sum of 10 consecutive integers, and the sum of 11 consecutive integers? So we're looking at the smallest possible integer a, so it should be minimal, that can be represented as a sum of 9 consecutive integers. So if we have 9 consecutive integers, they look like this: small a plus 1, small a plus 2, and the last one, because we have 9 consecutive, should be a plus 8. So it is a 9 consecutive integers, and a is the capital A is the sum of these numbers. Well, clear enough. So also it can be represented as a sum of 10 consecutive integers. So a also is a sum of 10 consecutive integers. Well, it would be very strange to assume that if a is a sum of these integers, so if we add one more, it will be also a sum of this, because this sum of these 10 consecutive integers is larger than this one, and they can't represent the same number a. Obviously, they speak here about some other consecutive integers, so a is represented as sum of other consecutive integers, b plus 1, b plus 2, and the last one here will be b plus 9. So I just write them separately, and I made this row a little bit longer because here we have 9 elements, here we have 10 elements. The sum of these equals a, and finally a can be represented as sum of 11 consecutive integers. So they look like c plus 1, c plus 2, and so on. Here we will have final one is c plus 10. So 11, 10, 9. And each of these sums represent your number a. So, well, obviously we have an arithmetic sequence here. And what is the sum of this sequence? We will use simple formula. First one plus the last one, a plus 8 divided by 2 times the total number of terms here is 9. So it is a formula for the sum. This one is 2a plus 8 over 2 is a plus 4 times 9. It is this sum, and it is equal to a. Also, this sum of this arithmetic sequence equals the same formula, first one plus the last one divided by 2 times 10, because you have 10 terms here. So here this sum 2 and 10, here you have 5, and this one looks like 2b plus 9 times 5, and again it represents your number a. And here this sum of this arithmetic sequence is the first one plus the last one, so it will be c plus 10 divided by 2 times the total number of terms here times 11 equals a. So this one is 2c plus 10, which is c plus 5 times 11 equals a. Well, we have 3 independent equations. Very important that a, b, and c here are integer numbers. And what should we do here? Obviously, we should equate as this one is equal to a and this one is equal to a. These two expressions must be equal. Therefore, we have a plus 4 times 9 equals 2b plus 9 times 5. It is our first equation. And, for example, 2b plus 9 times 5, 2b plus 9 times 5 equals c plus 5 times 11. C plus 5 times 11, it is our second equation. Does it make any sense to write the third equation as this one equals to this one? Very important to understand, it will not give you any new relevant information, because we already wrote that this one is equal to this one and this one is equal to this one. From these two equations immediately follows that this one is equal to this one. It would be redundant to write the third equation. You could do it, but you will not get any new information relevant for our problem. So let's simplify this. For example, 9a plus 36, here we have 9a plus 36 equals 10b plus 45, and here we have 10b plus 45 equals 11c plus 55. Well, as you can see here, the difference with 36 and 45, the difference is 9. That's why I want to write it like this. 9a minus 9 equals 10b. And here, 10b, this distance between 45 and 50 is 10. So it will be minus 10 equals 11c. So as you can see, I wrote it on purpose that we have 9s on the left side here and 10s on the left side here. Well, if you don't have experience working with integer numbers, for you it may look like we have a dead end here. Because look, we have one equation here, two equations, and three variables, a, b, c. However, the key here is to use the fact that a, b, and c are integers. Here you have the left side obviously divisible by 9. 10b should be divisible by 9. 10 doesn't have any common prime factors with 9. Therefore, b should be divisible by 9. So b should be represented as 9 times some k. So b should look like 9 times something. From here, which is just like simple conclusion. The same is here. 11c is divisible by 10, because this one is divisible by 10. 11 has nothing in common with 10, no common prime factors, and therefore c must be divisible by 10, and therefore c should look like 10 times m, where m is some integer number. And it is a very strong conclusion, so let's write it here. So b should look like 9 times k for some integer number k, and c should look like 10 times m for some integer number m. It means that what are possible options for b? So we can write it in a very simple way. So possible options for b are 9, 18, 27, 36, 45, 54, and 63, and 72, and so on. These are possible values of b, and possible values for c are like 10, 20, 30, 40, and so on. Well, we need to adjust b, that everything will work out. Exactly. We have this precise formula for a, and it looks like this. A equals 2b plus 9 times 5. We are looking at the number a that can be represented in the same time like this, and like this. And we are looking at the smallest number of a. It should be minimal. From this formula immediately follows that the smaller b, the smaller is the value of capital A. And if you take large b, of course, a will be also large. So if you want to find the appropriate value of b, it makes a lot of sense to start from minimal values of b. Because the smaller the b, the smaller the capital A, and it is exactly what we need. Let's look at b equals 9, and we'll figure out if it works for us. Let's substitute here. B equals 9. 18 plus 9, 27, times 5 is 135. So in this case, the value of a is 135, and it is the value of your a, and also it must be it can be represented as this one. So it should be represented as c plus 5 times 11, and we assume to find the value of c. So will it be some integer number? That's what we need. We need to find if it works for some integer number c. But from here you can see that 135 should be divisible by 11, and it is obviously not the case. I will remind you the very simple rule how to understand that the number is divisible by 11. You just take the sum of its digits with alternating signs. So you will take 1 minus 3 plus 5. If this sum is divisible by 11, then the initial number is also divisible by 11, but here we have that this one equals 3. it is not divisible by 11, so it means that 135 doesn't work for us. We will not get any integer c here, so b equals 9 didn't work for us. Let's go to the next option. b equals 18. b equals 18, substituted here, 36 plus 9, 45, times 5, 225. In this case, we should have an equation like 225 instead of a can be represented as c plus 5 times 11, and again 2 to 5 is not divisible by 11, so it's not an option for us, so this one goes away. 27 instead of b, this one is 24, I'm sorry, 54 plus 9, 63, 54 plus 9, 63, times 5, 315. So a is 315, should be represented as c plus 5 times 11. And again, 315 is not divisible by 11. 3 minus 1 plus 5 doesn't work, so 36 doesn't work. So we checked here, 36. No, we checked here this one. So 27 doesn't work. So now we are going to 36, the next option. So 36 times 2 is 72 plus 9, 81. 81 times 5 is 405. 405 instead of a. Again, it is not divisible by 11. So this one will not work for us. And once again, you should stay calm. So it's very important not to panic when you have several options that don't work for you. You should keep some patience, and it's very important to continue. And now we have b equals 45. Instead of b, we substitute 45. So this sum is 99. 99 times 5. You already, by the way, see that it will be divisible by 11 because 99 is divisible by 11. 99 times 5 is 495. So a equals 495. And I should divide it eventually by 11 to find c plus 5. And here I will write it like this. Instead of 495, I'll write 99 times 5 equals c plus 5 times 11. So it is the same as 495. And in this case, it will be way easier to divide because here we'll have 9 times 5 equals c plus 5, 45, 5, so c equals 40. It doesn't matter really what is the value of c. The main thing for us that c is an integer number. That's super important. And finally, we should also check that a can be represented in this way: a plus 4 times 9 for some integer value of a. So is it true that 495 can be represented as a plus 4 times 9? Here, the most essential thing that this number should be divisible by 9. In this case, a plus 4 is an integer and a is an integer. And obviously it is divisible by 9, really, because the sum of the digits here is simply 18 divisible by 9, and we don't even need to perform the division. We just know that a plus 4 will be integer, and therefore a will be an integer. Therefore, all these three representations possible for some integers numbers a, b, and c, and therefore the minimal value of a that we found is 495, and it is a correct answer for this problem. And now it's fully solved, and we are going to the next one. Okay, and the last problem that we will solve today is number 15, a problem related to geometry. So CH is an altitude of triangle ABC. Well, we need to make a picture. We need to draw something right away. So we have a triangle and an altitude. So this is a triangle and the altitude that looks like this. So altitude is CH, this one is C, this one is H, this is A, and this is B. Let B, R, and S the points where the circles inscribed in ACH, circle inscribed in this triangle, and circle inscribed in BCH in this triangle are tangent to CH. So you have two circles here. Let me try to draw it by hand. So one circle is inscribed in this triangle, and another circle is inscribed in this triangle. Let me use probably another color here, like this one. And you have two circles, okay? So, and are tangent to CH. And here it's very important to understand how you should read sentences like this. You see, the point R comes the first. If it comes first, then it's related to the first triangle ACH. So this one is point R, so the first point here is R here, and the second point is S, and therefore S is related to the second triangle BCH. So, and this one is S. So, and you also have that AB is 1995. Let me mark this one. So AB is 1995. This one 1995. AC is 1994, 1994, and BC is 1993, 1993, and RS, this segment RS, can be expressed as m over n. So it can be expressed as some fraction where m and n are relatively prime positive integers. Basically, you already reduced this fraction. You divide by any possible common factor, m and n, so they are co-prime numbers, and you need to find m plus n here. Well, the problem looks not very simple, but not complicated as well. So it's a very clear condition, and you need to find this segment RS, so the segment between these points RS. Well, if you have an experience in geometry, you immediately see that it's obviously related to the length of these segments between vertices and the point of tangency. There is a very simple fact in geometry, I hope you know it, that if you have an inscribed circle in a triangle, and you can express these segments between vertices and the points of tangency in a very simple manner. So let me remind you. So let's assume here we have a triangle, inscribed circles, and of course this segment is equal to this segment. It's obvious thing, right? This segment is equal to this segment, and finally this one is equal to this one. The main question, how to express, for example, this segment through the sides of your triangle. If this side is A, this is B, and this is C. The formula is super simple. For this segment, the length is A plus B minus C over 2. It's a very simple formula. I hope you are familiar with this one. It's very easy to understand why it works. Look, A consists of these segments, this one and this one. B consists of this segment and this segment. If you add A and B, if you add these sides, the sum consists of 4 segments. This segment, this one, and this one. If you subtract C, from these 4 segments, this one will be taken away and this one will be taken away. So what will be left is only these 2 segments. Really, you had sum of 4 segments. 2 of these are taken away, so this one and this one disappears, and the only thing that is left here is these 2 segments. And if you divide it by 2, you will get exactly 1 segment, so this one is the length of this segment. Similarly, for example, this one is B plus C minus A over 2. Very useful formula. Let's apply it here. And why I want to apply it? Because you can see RS is the segment that we need, is exactly the difference between HS, this segment of like tangency from vertex to the point of tangency, minus HR. HS is the segment from the vertex to the point of tangency in this triangle, and this one, HR, is a segment in another triangle, and RS is exactly difference between these segments. So in our picture, we can write that SRS is exactly HS minus HR. So, and each of these segments we can find, for example, HS by adding this side to this side minus this side over 2. The only thing that is very important for us, we just made an assumption that S is above the R. We have no idea how it is in real life. Maybe R is above S. So what to do in this case? We will just take absolute value of this difference, because really, if S is really higher than R, then this difference is positive and we will get the number we need. If it turns out that R is higher than S, in this case it will be like minus a length of this segment, and the absolute value will give us exactly what we need. So we will consider absolute value of this difference. Let's write HS from this triangle. HS equals CH plus BH minus CB. So CH plus BH minus CB over 2. Perfect. And HR is the segment, this HR, from the vertex to the point of tangency in the other triangle. And again, it equals HC plus AH minus AC over 2. So CH plus AH minus AC over 2. Minus AC over 2. So right away, when I subtract from this one, I subtract this one, you see that HCH cancels out right away. If you subtract, so this altitude will cancel out, and you will only have difference of these two minus these two. So I will not waste time writing this additional term. So I will write that RS equals this one, BH minus CB over 2 minus AH minus AC over 2, so absolute value. And after, like we have a common denominator, after working with signs, we will have the difference that looks like this. BH, B, so let me write B normally, BH minus AH plus AC minus CB over 2. Okay, plus AC minus CB, BH minus H. Yeah, everything is perfect. So let's look at these segments here. AC is the side of our triangle, is well known for us. Here BC, also well known for us. But here you have BH and AH. BH and AH also like segments. We don't know the value of these segments yet. However, how can you find, for example, BH or AH in this triangle? Well, the good news that you have all the sides of your triangle. It means that your triangle is uniquely defined. You can find everything. And usually what we do, we use cosine law. You find, for example, some angle, for example, like this one alpha, or like another one beta. You have no problems finding any of this. And let's assume that, for example, you know cosine alpha. After that, when you know cosine alpha, you can use this right triangle, and this AH is adjacent leg to this angle, and if you multiply 1994 by cosine alpha, you will get AH, and this is it. So it's very easy to find AH if you know cosine alpha, which you can find from cosine rule from this triangle, and it's in the same way if you know cosine beta, you will find BH, and it looks like you can find this value. However, the final obstacle here is that the sides of your triangle are pretty large numbers. If you try to apply cosine rule directly to these numbers, you will figure out that it's very difficult to square numbers like this, and the double product of these numbers, it's just not convenient to work with this one. It will be very difficult process. So in such cases, when you don't want to work with large numbers, usually what we do, we will introduce variables. So for example, we will mark this side 1994 as A, because this one is in the middle, and I would like to mark this one as a variable A, because this one will be A plus 1, and this one will be A minus 1. It's not necessary to mark this one as A. It's just up to you. It's your personal choice. I would like usually to mark as a variable the side that is like in between. So, and let's apply cosine law for triangle with sides A plus 1, A minus 1. Eventually, we will get our answer of this segment. It will be in terms of A, but when we have a final formula related to A, we will remember that A is actually 1994. We will substitute it and we will get our final result. So let's redraw our triangle. It has sides like this one is A, this one is A, this one is A minus 1, this one is A plus 1. So we're looking for this angle alpha. So A minus 1, A plus 1, everything is correct. So for this triangle, we apply cosine law, and A minus 1 squared equals this square plus this square, A squared plus A plus 1 squared minus double product A plus 1 times cosine alpha. Perfect. Let's work with the squares. A squared minus 2A plus 1 equals A squared plus 2A plus 1 minus, here I will not multiply them on purpose. I will leave it like this. It will be 2A, A plus 1 times cosine alpha. Perfect. As you can see here, we can get rid of this square, we can get rid of this one. Everything related to A we will bring to the other side. Or maybe not. We will bring this one to this side and this one to this side to get rid of negative signs. So we will have the formula on the right side 2A, A plus 1 cosine alpha equals A squared plus 4A plus 2. Perfect. And here we have that cosine alpha equals A squared plus 4a plus, I'm sorry, not plus 2. Of course, here we have just 1 cancels out. Perfect that I noticed it right away. I just, usually I try to check myself during the process, and it helps greatly. So a squared plus 4a, 1 canceled out, and you have simply that cosine alpha equals a squared plus 4a divided by 2a, a plus 1, a cancels out, and you have a plus 4, 2a plus 1. So cosine alpha is eventually this value in terms of a. Well, even if we wanted to get exact value for cosine alpha, it would make a lot of sense, as you can see, to work with numbers like a, and now we can substitute exact numerical value of a to find cosine alpha, but it's still, it's not time right now. So we will work with this one with beta, and we will get our final answer of this segment Rs in terms of a, and then we will make a substitution. So here we write another one, another cosine law for the angle beta. So a squared, this square of this side, equals a plus 1 squared plus a minus 1 squared minus 2a plus 1 a minus 1 cosine beta. Great. So here a squared equals, here double product, here with plus, here with minus cancels out, and we will have 2a squared plus 2 is the squares added, and minus 2, and we have difference of squares here, a squared minus 1 cosine beta. So this one goes to the left, and this one goes to the right. So 2a squared minus 1 equals a squared plus 2. This is it. And of course, we forgot cosine beta here times cosine beta. Okay, and here cosine beta equals a squared plus 2 divided by 2a squared minus 1. Okay, so we will leave it like this. It's our formula for cosine beta. And now it's very important that we can use, for example, cosine alpha to find AH. So it will be, well, it's very important for us to use it right away. So AH equals A times cosine alpha. So let's write it like this. A times cosine alpha is AH. So AH equals A times this one. It will be A plus 4, 2a plus 1. Perfect. And what about BH? It's a minus 1 cosine beta. So this one should be multiplied by a minus 1. And when it's multiplied by a minus 1, you see this difference of squares equals a minus 1 times a plus 1. So a minus 1 cancels out. And BH equals a squared plus 2 times 2a plus 1. Perfect, okay? And here, in this difference, when we are looking for RS, we have a difference BH minus AH. So let's look at this one. BH minus AH equals. So let's subtract these expressions. A squared plus 2, 2a plus 1 minus AH, it will be a plus 4, again 2a plus 1. Amazing that we have here already common denominator. By the way, we can also work with this. Look, AC minus CB. AC is A, CB is A minus 1. So it will be plus A minus 1. So it will be eventually, let's write it like this, plus A plus A minus 1. It will be the last one, all of that divided by 2, and absolute value of this expression equals RS. Yeah, let me quickly check that AC minus CB, yeah, everything is fine. So finally, we need to write this expression in terms of A. So the common denominator here, let's at first subtract these two. So you see that A squared cancels out here, and on the top we will have simply 2 minus 4a. So here we have on the top 2 minus 4a, yeah, correct, divided by 2 a plus 1, and here what cancels out? A cancels out, and you have simply plus 1, and all of that divided by 2, and again, the absolute value of it is rs. Here we multiply by 2a plus 1, so the total sum on the top will be 2 minus 4a, plus, I already expanded, 2 times a plus 1 equals 2a plus 2. Don't forget to divide it by 2a plus 1. All of that also divided by 2, and that's what we need. And as you can see here, we have 4. We have 4 minus 2a divided by 4a plus 1. Okay, 4. Let me check. 4 minus 2a divided by 4a plus 1, and also absolute value. And as you can see here, we made a great thing with this absolute value, because if you substitute here a, and the value of a is pretty large, here you will have a negative number, negative value. It means that this difference of segments, we subtracted hs minus hr, that it is a really negative number. It is a negative number, and it's very important to get this absolute value here, because it means that hr is actually longer than hs. So in the right picture, which is like reflects the real situation, r is higher than s, and s is lower than r. Nevertheless, let's substitute here a equals 1994. So we substitute here a equals 1994, and we will get our final result. Of course, here we should divide everything by 2. So it will be 2 minus a divided by 2a plus 1. You can see the fact that we introduced our variable a greatly simplified our solution. So now all the numbers that we have is simple numbers like this. So 2 minus 1994, and here we have 1994 plus 1 and times 2. Times 2, perfect. Okay, so this one on the top is minus 1996, minus 1992, and the absolute value will be 1992, perfect. So this one divided by 2, and this one is 1995. Okay, so this one is divisible by 2. When we divide, we will get 996 over 9919 and 5. So 996, yeah, perfect. So this one is obviously divisible by 3, and this one is divisible by 3. If we divide it by 3, we'll get 332 on the top. And if we divide this one by 3, I will need to do it manually. So it will be 6 minus 18, 19, 6 minus 18, and 15, 665, 665. And this is it. So as you see these numbers, probably there are no common factors here. Well, if you represent them as a product of primes, you will see that this fraction is irreducible. It is like your final step. You can't reduce it anymore. And it is the final fraction, m over n, and mn are coprime numbers, and m plus n equals, in your case, 997. And 997 is a correct answer for this problem. So that's the complete solution. It's very important for this problem at first to know the distance from the vertex to the point of tangency. This formula is super essential. So, and to use the right approach, and the right approach here to introduce variables and to keep it super simple, just to subtract one segment from another. Don't forget about the absolute value, because you don't know which segment is longer and which one is shorter. And after that, if you do everything correct, you will get the simple answer in terms of a. It will look like this. And after that, you will be able to quickly substitute numbers and to find that m plus n is 1997. So this problem is fully solved. And this is it for today. Goodbye.